Okay, so the CFP mentioned something about serverless and clouds. So this talk is about logging with serverless and clouds. So who I am. So I'm a software engineer at Lyft. My name is Paul Fisher. I've been working on infrastructure for far too many years now. And sometimes it seems like I keep solving the same problems over and over again. So most recently, I built out the current logging pipeline at Lyft. So I'll cover some of the history of monitoring at Lyft as well as the current logging pipeline that we're using there today. So some backstory. A lot of my work has been at startups experiencing kind of crazy growth curves. It's just kind of what I tend to go to. So as part of that, sort of before you have a few thousand microservices, you usually start out with a single application a handful of engineers are working on. And so we'll call that a monolith. And of course, you need some way to monitor that monolith. And so usually you start with logs, because logs are built into all of your language libraries, like pretty much regardless of what the language is. So in this case, this is some Python code, but we get a request, we log the request body, we process the request, get back a response, we log the response, return a 200. And sort of like the main thing that's going on here, like, which is also kind of annoying, which doesn't really scale very well, is that you're logging the entirety of the request and the response, even though it's a 200. So eventually you have some logs, you run tail on them, maybe you grep for 500s, you eventually call out to PagerDuty, throw in some bash as you add more servers, but fundamentally at the end of the day you end up with just tail, which doesn't really scale that well. So assuming that your monolith and your service has a bunch of growth, maybe because people decide that ride sharing is a good thing and pink mustaches are good ideas, eventually your logging visibility sort of looks like this. So tail is a really bad tool for telling you what's broken on your site, even if it's one large application. So you have this log hammer, and it's built into your language, so why not keep using it, right? So there are a bunch of companies which will encourage you to keep up this practice, and they'll give you dashboards and they'll generate metrics from all of this. And from those logs, they'll want you to ship them absolutely everything. Some of them will want you to downsample after you send all the logs to them. And so the fundamental problem here is that scaling strings and large blobs is really hard. And then additionally on top of that, so you have all these strings, you ship them off, now you have to run regular expressions on them. And you have to run regular expressions over and over and over again, and that takes a lot of CPU time. So once you move to this, and you can make this work, but if people still really like your service, and your service keeps growing, you sort of end up with a different type of fire, which is this one, which we talked about earlier. So it is possible to scale logs to handle absolutely everything. Like, you can do that. But it's really, really expensive. And I guess unless you work in the enterprise, because apparently they have as much money as they need, it's not really a good use of funds. So in our case, we think it's better to direct the funds towards the core business instead of just feeding this fire. So roughly at this point, you decide we're spending too much on logs, and it's time to implement a stats pipeline. And that's roughly when I joined Lyft. So we added a stats pipeline. Jan talked about that a bit earlier. And we started the effort to sort of move the engineering culture over from having logs to stats. So in general, stats and tracing should be your primary means of observing the state of your infrastructure. They're numbers and they scale. It's a lot easier to scale these. And so most importantly, which I guess a lot of people, well, something that we've had to work with the engineering org on, is that if your service is healthy and it's doing fine, you shouldn't need to log anything. Like, have as many metrics as you want about what's happening with your service for that 200, but at the end of the day, you shouldn't need to generate logs for that. And I talked about this a bit earlier, but please don't log every single request and response body that your service handles. It's pretty common that someone will spin up a new service, and they're testing it, they're debugging it, it's not in production yet, and so they want to log everything, and then they ship it to production without actually turning that off. So at this point, we're still growing as a service, and we need to reduce the cost of logging pipeline. And so this is a graph of sort of a generic logging pipeline. So you have all your services, they generate logs. You need to aggregate all of that so you don't overwhelm your database with like hundreds of thousands of concurrent connections. And then once you've written your data, you have to be able to search it, generate dashboards, and you have to alarm on it. So some of our constraints, the vast majority of our infrastructure is in AWS. And then for the pipeline in particular, we'd prefer that it be vendor neutral. So again, we can choose different vendors for different pieces if we have to move them around and or insource them. And one other sort of thing to note about this infrastructure is that it's sort of set up, it handles stateless infrastructure really well. And it's not really optimized for handling stateful problems. It's just sort of like how we've built the service out over the years. And in particular, our infrastructure looks quite a bit different on a Friday evening versus, say, an early Sunday morning. So it scales up and down based on load, and ideally we want the logging pipeline to do the same. So this is our current logging pipeline. The red circles, yeah, that shows up okay. The red circles are local infrastructure, and blue is everything that's serverless or in the cloud, i.e. not managed by us directly. So I'll cover all the connection points in a bit, but it's sort of the high-level overview. And in our case, we try to make sure that when a service writes a log entry, that it's available for searching in Kibana within about a minute. Okay, so the first stage. To get logs off of our servers, we use Heka. So it tails all the log files, aggregates the data into JSON bundles, streams them together, and ships them off to AWS Kinesis Firehose. For that JSON blob, we include a timestamp, the service that we're reading logs from, and the file path. And so there's an example of this on the slide, but it's essentially one JSON object per line. That's what that looks like. And one very common question I get is, why are we using Heka? Because it's been end of life by Mozilla, and somehow open source software stops working when it's been end of life. But it doesn't. So we used it for a prior project for proof of concept. It worked really well, and so we're like, why not reuse it for this project? And if one day we do have issues because it's been end of life, we can replace it. But overall, this has been one of the most stable pieces of the whole pipeline. It just works. And in the future, we're also considering other options other than just tailing log files, where we could inject data either with gRPC or protobuf, which Envoy uses for service-to-service communication. So we'd reuse that infrastructure for the logging side, but we're not doing that yet. Okay, so once Heka has it, it gets shipped to the AWS Firehose. So every single instance that we run on AWS is connected to the Firehose. So all that data gets aggregated together and written in real time to S3. And the S3 storage is our permanent archive of all the data from our servers in this case. So AWS gives you a few toggles that you can change on this that determines how often it flushes to S3. In our case, we never hit the per second modification lag option because we're always writing enough gigabytes where we flush based on that. So it's always less than 60 seconds for us in terms of flushing to S3. The Firehose also compresses data. It's really super cheap. And so far, we haven't had any issues with scaling it or having Amazon up the limits to keep up with our growth. In particular, the Firehose has this really neat property that they will retain all data for up to 24 hours if the downstream service is not available. In this case, that would be S3. So for the outage that happened earlier this year, multiple hours, our logging pipeline was down, but we still had metrics and tracing available. So all of our core systems and alerting, all of that was working fine, but our logging pipeline was temporarily down, but the pipe from Heka to the Firehose was working fine in that sense. was getting 200s as OKs, everything's in Firehose, and it just gets buffered. So as soon as S3 was back up and running, then the Firehose flushed everything out. And sort of interesting story, we did contact AWS when S3 came back up, and they're like, hey, can we please flush this faster? They said no, just because like every single customer and like, yeah, essentially like S3 was going full out when it came back up in terms of like capacity. So yeah, it took a little while to flush. I seem to recall it was like on the order of like an hour or so. And then all that data ended up making its way through the rest of the pipeline. Okay, so some stats on the Firehose at Lyft. So we shove around 10 gigabytes per minute into it. And there's also this metric that AWS keeps called data freshness. It's sort of, I guess roughly you can think of it like P99 or P999, where this is like the oldest absolute record in the Firehose that is yet to deliver to S3. And that stays around 20 seconds or so, but most data ends up getting written to S3 before that. Okay, so the next piece is Lambda. And if you're not familiar with that, Amazon has a service where you can write a function in one of a handful of languages. Python's one of them, so we use that. And then they'll just schedule that function and run it as much as it needs to run. So some other constraints, execution time cannot exceed 5 minutes. So if you're doing some operation and it takes more than 5 minutes, they'll just hard kill that function call. It's also guaranteed that you'll never have concurrent invocations on the same machine, where a machine is probably implemented as containers on their side, but it has some nice properties for when you're writing your function that you don't have to worry about multi-threading or something else stepping on top of your function that's executing. So the pricing for Lambda is really, really, really cheap. And they bill in terms of increments of 100 milliseconds at a particular memory footprint. So in terms of like when you're setting up your Lambda and in terms of how it's billed against you, CPU doesn't come into the equation. It's all based on memory. But the CPU scales with the memory footprint. So for example, if you go from 128 up to 256, then you get double the CPU, and it doubles the cost of that particular 100 millisecond increment. Okay, so we use Lambda for, the main function that we have in Lambda is our log ingest. It parses a single Firehose bundle on S3, one at a time, and it stays CPU bound because it's really just doing a whole bunch of string manipulation and shoving data around the network. So one kind of particular item of note, which is not necessarily immediately intuitive, is that because we're CPU bound, we can actually increase our per 100 millisecond cost. So like, for example, if we like double that, that also doubles our CPU, which means that we have the amount of time that it takes to process that packet. So we've made the pipeline faster, and our end cost for running that function stays the same, even though everything's been sped up. So yeah, overall, we fit into the smallest Lambda that's available, which is 128 megs. We don't run at that because we want more CPU. So again, so we can like get through the pipeline faster. But the way Lambda does billing, they calculate based on resident size of your application or your function and how much it uses. So it doesn't take into account the page cache. So we stream to disk a whole bunch as part of our operations, and that ends up being really fast and doesn't really use any memory. So we pull a file down from S3, we save it to a temp file, we kind of fan that out, I'll talk about that in a second, and we ship it back off to Elasticsearch. And here's like a random CloudWatch graph. So where we get like 10,000 invocations per hour roughly. But essentially, at whatever rate the Firehose is writing bundles in S3, that's how often our Lambda function gets called. Okay, so kind of going more in depth into the Python function. So this is the basic flow of our Lambda function. So nested write occurs, AWS calls our function. So it goes into the Lambda handler function there. So we pull down the S3 bundle, we decompress it, we parse it into JSON, then we break it into multiple temp files per Elasticsearch document type. So this all like fans out onto essentially the temp file system. And then we use requests to stream it back into Elasticsearch using the bulk API. Okay, so this is sort of the core of our logging pipeline. So in addition to talking to Elasticsearch, our Lambda function also talks to SQS, where we store state for failure cases, as well as Dynamo to keep track of per service ingest rates. So we can do rate limiting. Okay, so here's a list of a whole bunch of properties that our function has. So we're almost entirely stateless for Lambda, which works out well, because Lambda doesn't deal with state very well. So our function processes at most 2 bundles any one time. The goal is like we have to be done within 5 minutes. Ideally, we want to be done way before 5 minutes is up. And in the normal case, we only process 1 bundle. So when Elasticsearch is having issues, we found it's best to not keep hammering it. And it's best to sort of like, as soon as you realize there's some sort of disturbance in the force, to back off and give Elasticsearch a time to either heal itself, move shards around, whatever it's doing, and get into a better state. So if that happens, where we're getting some amount of back pressure, depending on how bad things are, we'll either might retry once with the hope that we get another node that's up and is working well. But if it's not, then we write the name of the bundle, so it's only a very small amount of data, to SQS. And so that's basically a work queue there that we have to backfill later on. So one really, for this whole system, sort of like one of the properties that I think is kind of the coolest is we get sampling for free. So we have Heka and the Firehose are all sort of like combining data together sort of randomly, concurrently in real time. So the end result of these bundles that get written to S3, it's sort of a random mishmash of everything that's going on in the system. At any given time, there's no like particular ordering other than the time. So if we get a huge spike in load all at once, and Elasticsearch can't handle the full write load, then whatever data ends up making it into Elasticsearch for that given time window, that's the data that Elasticsearch has. And that's usually enough data that we can triage and debug what's going on. And so anything that doesn't get written while there's a problem, that all gets pushed back into SQS so we can automatically backfill later. But it doesn't mean that in sort of situations where there's like huge spikes or something happens where ES just can't keep up, then we have enough data where we can triage and figure out what the problem is. There are other logging systems that try to be, I guess, perfectly consistent, where if they get overloaded with the amount of logs that are going into them, they'll just start falling back in time. So, as an example, we've had situations in the past with like older systems where there's this huge spike and our logs are delayed by like 15 minutes or half an hour or something like that, which isn't really useful because then you're trying to like debug what's going on and all your data it's not now data, which is what's important for triaging. So this is like a really useful feature. So again, I mentioned that we write to SQS when there's an issue. And so what we do is the next time, so since we try to be stateless, the next time that we run a Lambda, if its connection with Elasticsearch is perfect, so there's like no issues, no blips, no retries, no nothing, then we'll take a work item from SQS and then process it. So at most, we run it roughly 2x, I guess you could say. So you always have the current bundle that you're trying to put into Elasticsearch. And then if that goes well, then you also can pull off from SQS and process one more. So it's like 1 or 2, and then you're done. And more recently, we added rate limiting. And this is to handle the case of where, usually the case is a developer adds a log entry inside a really tight loop, and they ship it to production. And so in this case, they just shoot themselves in the foot as opposed to the rest of the engineering org and all the other services. So this is all based on Elasticsearch 5. We have time-based indices. So we have a cron lambda, which runs once a minute. It's pretty simple. And it carries out all the recommended maintenance operations. Elastico has a blog entry on this, and our cron essentially implements it. That's what's in the paper. So roughly every hour or so, we roll over our active index. Then we move it all the shards to a single node. We shrink it. Then we force merge, maybe, it depends. And then this also cleans up when we need to free up some disk space. So Elasticsearch is really great, but it only speaks JSON. So prior to moving to Elasticsearch, we had a handful of different on-disk logging formats. So in our Lambda function, it has this property where if it gets a log that it doesn't know about, it'll try to figure out a timestamp from those logs. If it can't find a timestamp, then it'll take the timestamp from the Heka bundle, because that's a JSON blob that has a timestamp on it. And then what we do is we increment the number of milliseconds for every line within that Heka bundle. So at least if you're looking at logs in Kibana, they'll be correctly ordered. So we've been moving everything over to a structured logging format. This is an example of what it looks like in Python. So we just extended the base API to take a key value argument, which is a dictionary. And you can put anything in there that's serializable in a JSON. So as an example, it's fine to have a dictionary within a dictionary. And then on the bottom is what it looks like on the system itself. So if you are still using tail, then that will work fine if you're just looking at logs. So there's nothing too special here. We use Kibana. It works okay. It's hosted by Amazon. So yeah. So one sort of interesting caveat about Elasticsearch, at least the hosted version that Amazon runs, it runs on the public internet. And so in order to communicate with it, because you want to lock it down because it's on public IPs, you either have to cryptographically sign your HTTP requests, or you have to whitelist by IP. And we have a cluster of authentication proxies in our VPC. They just run Nginx as a reverse proxy. And there's a Google authentication in front of that, so engineers have to authenticate before they can get to Kibana. And one other nice benefit of this is since Kibana doesn't know what a user is, because they have to Google authenticate, then we at least can associate queries and entries requests with who the user is. And then Amazon has a full white paper on how to set this up in order to talk to Elasticsearch. For logging, we keep metrics on all the different log levels. So if the logging error rate spikes for a particular service, we can page via our standard metric setup. So we don't actually need the logging system to page someone if logs go crazy, because the metrics pipeline handles that. There are a handful of cases where we do need to alert based on the content of logs. There are a whole bunch of cases where monitoring just standard system OS logs. And so the security team gets paged for things like that. So we use LastAlert. It's written by Yelp. It's open source. It works okay. We're not terribly concerned about the system being highly available because so much of our stack we depend on the metrics pipeline. And so this mostly works. It's fine. But if it does blip, all of its state gets stored in Elasticsearch, and Elasticsearch should be highly available. So it just comes back up and picks back up where it left off if we have to stop it or start it. Okay, so on to scaling Elasticsearch. For AWS, if you're used to AWS or you've used it, for any web form element, you always want to scroll all the way down and all the way to the right. And if you get into a state where you can't go down any further and you can't go right any further, then you should contact your AWS rep and ask them to add more options to that particular web form. And so as far as Elasticsearch itself goes, like standard scaling rules apply. Usually you want to start with a large cluster and sort of scale down to find out what works. In our case, we found better performance from running smaller clusters with larger capacity instance types rather than big clusters with smaller instance types. One thing to note is that when Elasticsearch moved to version 2, they started to implement ACID-like database properties. We don't care about that at all for logging. So in our case, like, we really, really, really want to set async mode because performance is really bad if it's not async. It's close to useless in our situation. Because we use it mostly for triage, and it's sort of best effort, if we have a few seconds of data loss because we lose a node and it comes back or whatever, that's okay. In the worst case, we can backfill from the S3 bundles. Some other notes, you probably want to use local storage as opposed to EBS. That kind of depends. And then if you can, having multiple clusters, separating them out by document type might be more useful. In our case, we have one really large cluster, which we sort of use for triage that all systems go into. And then another example is we have a separate security cluster, which has a much longer retention period and has less load on it. So our original cluster that we built for this pipeline, 10 nodes, a whole bunch of RAM, and a whole bunch of page cache that we use the RAM for. So this would do about 10,000 JSON documents per second. We have a whole bunch of fields because the monolithic application that I talked about earlier, it natively logs in JSON and always has. So we burned through a lot of fields as part of that. So all this was working great. We survived New Year's this past year with this pipeline, worked fine. Then like growth has still kind of been kind of crazy. So more recently, we sort of like got back to this state. It's not quite as bad as before, but we're having to rely more on SQS back pressure, and we're having to like scale the cluster more. So it's kind of the state that they're in right now is in terms of scaling Elasticsearch portion of this up. So the available managed Elasticsearch services are mostly designed for homogeneous clusters. A lot of them are designed more for the database use cases where you do want ACID-like properties. And so logging tends to be more of a specialized use case, even though it's not for this conference or for us. And so depending on your vendor, you might have issues with support response time, or you need access to Elasticsearch logs, or you need to run perf, or you need to add a bug fix, or you need a new version to upgrade. So there's a whole bunch of use cases of why you might want to insource Elasticsearch or use or use a different vendor. It's just one of the pieces that you might want to move around. And so that's what we're currently exploring, that option of insourcing the Elasticsearch component. So as an example, this kind of comes from Elastic's blog on like the sort of like best practices in setting up a logging cluster, and that you want hot nodes for your ingest, and then you want a different type of node that just handles reads after you do, say, your hourly rollover or so, and then you might want to have cold nodes that do nothing but leucine segment merges. Okay, current status. For metrics, we're doing, Jan talked about this earlier, we're doing about 20 million metrics per second with either 60-second or 1-second rollup. On the logging side, we handle about 15,000 JSON documents a second. And overall, I'd say we've done a reasonably decent job of moving the organization from logs over to metrics. And I guess it's roughly around like 1,400 metrics for every log event that we write. So in conclusion, use metrics, not logs. And if you must use logs, serverless works pretty well. Thanks.